Thank you. Okay, today is April 20th. Is that correct?
Yeah.
Or 19th? 19th, actually.
19th. Oh, yes.
All right, good to start out getting the day wrong. And 2012, and we are going to talk about more fun with zeros of polynomials. I have two new ideas. Actually, I'm not sure how new they will be to you today. We'll find out. First idea. Yesterday we talked about finding the real zeros at the factor of the last number. But if you have a polynomial, if your polynomial looks like this, px to some power plus ... x to the n minus 1, x to the n minus 2, etc., all the way down to a final number q, whatever that q may be. Never sure why math books picked p's and q's for this.
Was this like the extra credit with p's on it? Like that?
No, that was something else.
Or that was like conics or something.
Yeah, that was something. I do want to go over that at some point actually, but that was something totally different. There's only so many letters math likes to use over and over again. Then all of the possible, your possible rational zeros are plus and minus all the factors. Did I do my P and Q backwards? Remember how the book does it? For how you learned it last year?
I think you have. Yeah.
For the P's and Q's, you guys learned this last year?
I don't remember that.
Okay, well the way I have it written here, and this may be different, is it's going to be all the factors of Q divided by all the factors of P. I apologize if it's backwards from what you heard before. The point is, if you have a coefficient at the beginning, okay, remember yesterday we just checked factors of the last number, okay? If you also have a coefficient at the beginning of your polynomial, after you've arranged them all in descending order of degree, this is the degree of the whole polynomial, your other possible zeros also include the factors of the last number divided by the factors of the first one. So I'm just going to make one up real quick. If I have, for example, f of x equals 2x squared, 2x cubed, minus 5x squared, plus 3x, minus 8. Now yesterday, what factors would you have guessed might give you real rational integer zeros?
Plus or minus
2,
1, 2, 4, and 8.
Yep. 1, 2, 4, and 8, right?
Yeah.
Well, now you'd have to include plus or minus 1 over 2. And you want to think about, you want to check the rest of them. You'd also have to check plus or minus 2 over 2, dividing by this leading number. But what is 2 over 2 equal?
1.
So we've already taken care of that up here.
Yep.
Plus or minus 4 over 2, that's the same thing as 2 we've already taken care of. Plus or minus 8 over 2, that's the same as the 4 we've already taken care of. So your new possibility would just be 1/2.
Oh, we did do this last year.
Okay, I didn't think it was brand new, but for some reason I'm thinking it was P over Q in Algebra 2. The point being, you start the same way, but if there's a leading coefficient meaning on for your first term, when you've arranged them in descending order of degree, third, second, first, 0 degree term, then you have to take all the factors of the last number and also divide them by your leading coefficient and check those factors as well. In this case, that would only give me two new possibilities, 1/2 and negative 1/2. And then you do the synthetic division with the fraction, and it's more annoying.
So you're crossing out the other ones because those are the same as the ones above?
Correct.
Okay.
Correct. So these are, and sometimes the directions might say just list all the possible real zero or rational zeros of a polynomial, and all you would need to do is write this list, and that were the case. If it were to find the factors or find the zeros, you'd start guessing and plugging them in. I've tried to be careful to make sure you know when you're only checking for integer zeros and only checking for rational zeros. Are those the only possible places that a polynomial can hit an x-axis? Is there any reason a polynomial can't hit an x-axis at the square root of 17?
There's a discontinuity?
No. There's no discontinuity. Remember, polynomials are always continuous.
Oh, yeah.
Remember that rule. If your polynomial does hit at something that can't hit the x-axis at a point that can't be described as a fraction, which is the whole definition of an irrational number, remember. And remember, every square root that is not of a perfect square is an irrational number. If it hits at one of those places, this will never find it. This will never work. So how do you even know to look for these? How do you even know that you've missed a few? Aren't you curious? That's the point where you're supposed to all say, how would we know?
You're going to teach us.
I'm going to teach you, right. Okay, so follow me over here. And there's two ideas that I need to give you, both of which I think you should have seen before. The first one is called, of all things, the fundamental theorem of algebra.
That's really vague.
That is really vague. And it's
Has
about,
the word fun in it.
it does have the word fun in it. It must be fun. It is about
And
polynomials.
mental.
That's right. And it says, simplifying the phrasing a little bit, this first part seems simple, then it gets complicated. A polynomial has the same number of zeros as its degree. So this seems simple. If it starts with x squared, it's got two solutions, and it's a polynomial. Can't have any weird exponents, fractions, negative exponents after that. If it starts with x to the fifth, it's got 5 solutions. This would seem very helpful except for one thing. This theorem has a corollary.
Wait, there's no apostrophe S. Sorry.
You're right, it's possessive. Possessive is no apostrophe.
Correct. Sorry, I'm weird.
No, double check.
Booth would be proud.
I used to know these things back in the day, and I need to keep up with them. Here is the thing that makes this less confusing. If you're really thinking about the shapes of polynomials you've seen, you might have already seen that there's a flaw in this. But here's the flaw, as it were. Not all the zeros are real.
Oh, that's annoying.
Because you may have noticed that, because think about it, has every parabola you've ever seen always hit the x-axis?
No.
No. Because if this were all I wrote, a polynomial has the same number of zeros as its degree, if that theorem were always true, this quadratic, this parabola would be impossible. It would have to hit the x-axis twice. Quadratics that sit on the x-axis would be impossible. But this theorem works, except it includes I. It includes the square root of -1 among its possibilities. If you count the imaginary or complex solutions, this has 2 solutions. Every cubic has 3 solutions, but you have to count the imaginary ones. One way that's phrased is, another way this is phrased is a polynomial of nth degree has n, oops, started to skip the word, has n,
What's nth degree?
like if it's starts with x cubed, it's 3rd degree.
Oh.
Starts with x to the 7th, it's 7th degree. Has n, that same number, complex solutions. Because complex means, well, it means a plus bi, with this being, remember, the real and this being the non-real part.
Wait, what did we do? We did something earlier in the year where we had to write something in the form of a plus bi.
We did polar complex. Remember, we did a plus bi and we converted it to cis, cosine plus I sine, all that kind of stuff. The thing is, when you say n complex solutions, you're including the real ones. So for some of these a plus bi solutions, this b could be 0, and it might just be real. So for example, on this parabola, which does hit twice, okay? In both these cases, this would be said to have two complex solutions, but since you can see that they're both real, you know that b is equal to 0 for both of them, and it's a plus 0i. In other words, you can forget about the complex part. So every polynomial has the same number of solutions as its degree. The problem is, some of them aren't real, and we're not going to care about those. Like if you're graphing this in 2 dimensions, you don't care about the imaginary solutions. So how do you know how many to look for? How do you know how to just find the real solutions? There's one more piece to the puzzle I'm going to give you. You guys get this idea? Okay, follow me back over here, Tyler. Did you hear that in Algebra 2? That polynomials always have the same number of solutions as its degree, but some of them have i's in them?
No.
Okay. So that would be a pretty useless piece of information if you're just looking for how many times this polynomial hits the x-axis, because the i's don't count to help you with that. Here's what makes this a little bit more helpful. And this is called Descartes' rule of signs. And Descartes' rule of signs gives you another hint, not an absolute answer, but another hint as to how many real zeros, actual intercepts you're looking for. Okay? Step 1 with Descartes' rule of signs. Write the polynomial in standard form. What do you think that means?
You need to do it, but I mean, you just make sure it's in descending order, like, so cubed, squared,
Descending
x.
order of the exponent of the degree.
Yeah.
Very good. That's a good way to put it. I know where you were going with it. You were trying to remember my definition of it, the ax to the n plus a sub 2, x to the n minus 1. Yeah, all that kind of stuff. I'm going to go with Jen, standard form. Just make sure the exponents go down right to left. 2, count the number of times the terms change sign, as in positive or negative. Okay? The number of changes minus an even number
Is 3, right?
give you your possibilities. Well, that's just part of 2.
Yeah.
So,
Wait, any even number, or?
well, yeah, see, that's the thing. Like, let's say the signs change 5 times. Then you either have, or 0 it could be actually. Then you either have 5, 3, or 1 positive zeros. And this gets you just your positive zeros. So you know you have 5, if you get 5 sign changes, you know you have 5, 3, or 1 sign changes. If you get, zeros. If you have 4 sign
So
changes.
it doesn't matter the actual number you end up with, it's just the sign that matters? Is that it?
No, it's the number tells you how many times it hits the x-axis on the right side. So for example,
No, I mean, for the where you're saying positives, it doesn't matter that minus that. The answer, you're just looking at the sign.
no, the answer to this is going to be in a number. It's going to be a whole number. It's going to be positive. You're counting something, so it's going to be a positive integer or 0. Okay? Whatever that is, that number minus 2, that number minus 4, that number minus 6, however long it takes you to get down to 0 or 1, those are your possible choices. This will be clear after I do an example of it, but I want to get all the rules up first. Then, find f of negative x. Put a negative. Assume x is a negative number. And adjust your terms accordingly. What I mean by that is, if you assume every number is negative, so what happens when you square a negative?
Positive.
What happens when you cube a negative?
Negative.
Okay, so if you put a negative x into a term that's cubed or to the first power, that's going to switch the sign of that term. If it was positive, it'll make it negative. If it was negative, it'll make it positive. If you put a negative x into something to the second or fourth power, that won't change the sign, because it'll stay positive or stay negative. Again, I'll do an example for this. Then you do the same thing. Count the sign changes. And once again, the number of changes minus an even number gives you all of your possible negative real zeros. Now this will only help you with the real ones. If all of your zeros are imaginary, well, this may help you figure that out. This will help you figure that out, actually. I don't expect you to see how this applies yet. But take a moment, look at it, and as I go through an example, I'm going to refer back to all these rules. I wanted to have them all up before I started my example. Any questions on anything I've written up here? Any of the words not make sense? All the words are in English, right? All right, Tyler, follow me back over here. Okay, now, for example, and I think I'll steal this one from the book. Okay. F of x equals 2x to the 5th plus 3x to the 4th minus 6x cubed plus 6x squared minus 8x plus 3. As I break things. Okay. This might have helped you with your guessing last night. All right. First term, is the leading coefficient positive?
Yes.
Yes, hope that was everybody getting that one. If this is plus 3x, is that a change?
No.
No. If I go to plus 3x to minus 6x, do I have a change in the signs?
Yeah. No. Wait. Yeah.
Positive to negative, yes. If I go from minus to plus, do I have a change?
Yes.
If I go from plus to minus, do I have a change?
Yes. And the next one is yes.
Switches every single time. So I have 4 sign changes. This means I either have 4, 2, or 0 positive real x-intercepts. Here's the value to knowing this. The trick I just mentioned again with the p's and the q's, and the trick we did yesterday with looking for all the factors of the last number, those can only help you find rational zeros. They can't help you find irrational ones. This can help you determine if those zeros exist or not. Okay?
Wait, Mr. B,
Yeah.
4, 2, and 0, how are you getting?
Take the number of sign changes and subtract multiples of 2, even numbers from them, until you get to 1 or 0. Because you can't have a negative number of zeros.
Wait, can you write that down somewhere? Sorry.
Okay? So,
What do you mean negative, positive, real x-intercepts?
4 minus multiples of 2 equals number of changes. Okay, here's the deal. Noah, to yours. Jen, is that helpful?
Could you
Yeah,
have
thank you.
subtracted 4?
Hold on. Don't try to do any algebra yet. This is all very like, you're getting into that math where you're like trying to determine if a solution exists. We're not even getting to finding what the solutions might be yet.
I was talking about where you subtracted 2 to find.
Oh, I took a 2 away,
Yeah.
and then I took 2 more away.
Could you just do 4 from the start?
Sure, but you have to consider this possibility in the middle.
Okay.
You always have to consider each multiple of 2.
Oh,
So 4 is a possible. See, 4 is a possibility, 2 is a possibility, and 0 is a possibility.
So it wouldn't be like plus or minuses for each
That- Nope. These are just the positive zeros. So this tells me, Noah, that either this polynomial never hits the positive x-axis, possibly it hits it never, or maybe it hits it twice, or maybe it hits it
No times at all.
1, 2, 3, 4 times, or not at all. But those are the only possibilities. I know for a fact it does not hit this x-axis 3 times. I know it doesn't hit it 5 times. I know it doesn't hit it once. It has to hit it. If you follow Descartes' rules of signs, I know that I must look for I have to look for either 2 or 4 or no zeros over here. So let's say then I start looking at all the factors of 3 divided by all the factors of 2, and I only get 1 time that it hits the x-axis. I know I've missed one. I know there's another one here. Maybe I've missed it because it's irrational, because it's like a square root of 5 or something. Does that make sense?
Yeah.
So if the trick we do yesterday gets me 1 x-intercept, I know I've got to keep looking for another one. If the trick we did yesterday gets me 3 positive x-intercepts, I know I've got to keep looking for another one. There must be 4 then. If the trick I did yesterday gets me 5 x-intercepts, I've completely messed up somewhere because there's no way for there to be more than 4.
Wait, so can you write that down? Sorry. Wait,
I'm not sure how I would sum all that
No,
up.
wait,
I'd like
what
to.
is, what is your name for what we did yesterday? That's synthetic to be like.
That was using synthetic. That was applying the remainder theorem.
Okay.
So this, you can think of this first off. The first use of this is you can use this to double check the results of the remainder theorem. And also to expand on the results of the remainder theorem. It's possible that you only found 1 positive 0 with the remainder theorem because the other zeros were irrational. The remainder theorem will never help you find a 0 that is the square root of 3 or the square root of 7. You know what I mean about that? So that's an important distinction. This, however, will tell you that those zeros might be out there.
So like if the remainder theorem gives us
1 positive x-intercept.
okay.
Then I know that I'm missing either, okay, I know there's not 0 positive intercepts. I know I have to look for either 1 more or 3 more.
Okay.
I don't know which from this. This isn't very precise. It's always accurate. It's not precise. The best result for this, Jen, is the remainder theorem gives you 3 zeros, and this tells you have to find a 4th. Because then there's no other possibility. Now, what we just did only helps us on the positive x-axis. Only on the positive x-axis. If we want to know what's going on the negative x-axis, Tyler, can you see the whole over here as well? Okay. For the negative zeros, rational or irrational, but not non-real, won't help with the imaginary ones. Now I have to look at f of negative x. If I put a negative number into x to the 5th, will that final result be positive or negative?
You put a negative number, that's
Negative.
Yeah, if I raise a negative number to an odd power.
Oh yeah.
So if x is absolutely going to be negative, this is going to be negative 2x to the 5th. If,
And then all the signs change. You're saying.
not all of them, because what happens if I raise a negative number to an even power?
It stays positive.
Stays positive. So if I put a negative number into x to the 4th, that doesn't
Oh.
change. If I put a negative number into x cubed, do I get a positive or a negative result?
Then positive.
Well, I get now if I cube a negative,
Negative.
negative times a negative is a positive, times a negative again is a negative. But then if I subtract that negative, that will become positive.
Yeah.
Yes, the final result here, right, the sign will change to positive, but cubing a negative keeps it negative.
Yeah.
If I put a negative into a positive, I'm sorry, into an even exponent, it comes out positive, so that sign won't change. If I put a negative in for x, what will happen to that subtraction?
That'll become positive. And then that's just negative.
Plus 3 won't be changed by that,
Why?
because I'm not putting anything in for x.
Oh, right.
Oh, I think I see this one.
Okay, so now, hold on a sec. Okay, now I have to do this process again. Negative to positive, is that a change?
Yeah.
Yeah.
Yes.
The rest of them are no.
Positive to positive, positive to positive, positive to positive, positive to positive. No more changes.
It's the reverse of the original.
In this case, the pattern, you won't always get it perfect. Don't count on that every time. Right. So there's no more sign changes, so there is one sign change. Now, it's the exact same rule. Whatever number of changes you get here, you take this number and you subtract 2 from it until you get to 0 or below. I can't subtract 2 from this at all. This is helpful. This tells me there is exactly one negative solution, one negative 0. And it is real. It is not complex. It's just the real part of it, okay? So there is one. So I know for a fact, if I don't find at least one x-intercept over here, it must be irrational if I've done the remainder theorem correctly, but it's got to be there. So I know I can go looking for it. That doesn't really help me over here. That doesn't narrow my choices down. Like if this had been 3, I would have known that this 4 was impossible because you can't have more than 5 solutions total. This is like puzzle solving. It just helps you narrow down your choices. Does that make sense? So that is how you can know how many you're looking for. Let's find these zeros.
Yes, let's.
Alright. Alright. Tyler, come back. Alright. What are my possibilities?
For f of x?
Yep.
2. Oh, no, wait. Oh, for
So what are the factors of my last
One
number?
and 3. Negative 1. Negative plus or minus.
Plus or minus 1 and 3. And what about that first coefficient? Means I have to also check plus or minus.
Minus 1/2 and plus or minus 3/2.
Yep. That's all plus or minus. I'm writing it funny today, sorry.
Let's roll with 1.
Now, we know that one of them is negative. We know that 0, 2, and we know that there's either 0, 2, or 4 positive ones. But who's got a first try?
Let's go with 1.
Positive or negative, Tyler?
Positive.
Positive 1. My coefficients are 2, 3, negative 6, positive 6, negative 8, and 3. I did make sure you get your coefficients from f of x and not from f of negative x.
Yeah.
That would be an easy and silly mistake to make. Alright, bring down the 2. 1 times 2 is 2, 5, 1 times 5, negative 6, negative 1, negative 1, 5, 5. Nicely done. Somebody's lucky today.
He's always lucky.
Well, yesterday was
Now sometimes you get something helpful from this, because this now tells us that we're really looking at x minus 1 times 2x, what do we start with, cubed? Fifth, haha. 2x to the fourth plus 5x cubed minus x squared plus 5x
Minus 3.
We didn't get as lucky as I hoped to this time, because sometimes, well, you're never going to with 1. With 1 that won't happen, unfortunately. If you use something other than 1, you'll get a different last number, and then you'll get fewer zeros. But this time we have the same number of other zeros to play with, and this is a 4th degree. So now we look at this one, and well, okay. Is there any chance, we've also found that one of the zeros is x equals 1, right? Is there any chance that's the only positive zero? Is there any way that can be the only positive zero?
Yeah, if we only have, don't we have to do that test to see if that's the only one?
Good. Well, we already did the test for the whole polynomial. Okay, we're not going to create new zeros here. Okay, so according to Descartes' rule of signs, this polynomial can only have 0, 2, or 4 positive x-intercepts. So is there any way that this could be the only one?
No, because it's,
No.
It's just small.
So we could eliminate 0 as a possible number of positives. So we know there's at least one more positive one, possibly 3 more positive ones. But we don't know if this method will find them all, because it might be irrational. Okay, what about, give me another number then.
1/2.
1/2. Not afraid of the fractions. I love it. He's looking for another
awful.
positive
No,
one.
I don't want to do one.
Now, oh, but wait, do I have to do 1/2 on my original?
No.
No, I can do it on my
Yeah.
remainder factor here, on what I got as my answer down here. So I can at least do it a little bit less, Jen, if that makes you feel better. I don't have to multiply as much by 1/2. Bring down the 2. 1/2, 1, 6. Half of 6, 3. 2, 1. Who said 1/2?
Me.
No.
Nice.
Everybody's even one.
Double check me, though. Is that right?
Let me just do it.
1, 6.
Yeah, they're looking at this example. Okay, now, that means I now know that f of x actually equals x minus 1 times x minus 1/2 times, what are we down to, 4th? 2x cubed minus 6x squared plus 6x squared plus 2x
Plus 6.
plus 6. Hey, how many sign changes does this remaining factor have?
None.
So how many positive x-intercepts does this have?
Real.
Remember, Descartes' rule of signs says your number of changes tells you how many real zeros you have. If you have no changes, how many real zeros do you have? None. There are no more. I can look at this and say, no positive, I don't know about negative, no positive zeros.
Wait, how are all those smushed together?
Okay. Our original function is on the other board,
Yeah.
over there. When you get a zero remainder, Jen,
Yeah.
you've proven that x equals 1 is a 0,
Yeah.
and that x minus 1 is a factor.
Okay.
And then this tells me what's left.
Yeah, but why is that together with that? Like, what? Those are just the same. Those are both answers.
Yeah, well, I'm continuing to factor the original polynomial. So first I proved that it was, or you guys proved, I didn't make these guesses, because I'm luckier than I am with this, that the original could be rewritten as x minus 1 times my new polynomial made from these coefficients. Then 1/2
So you're
works.
just using x minus 1 in that one? You're not
Yeah.
using the
I'm
other
just-
thing?
Well, I'm bringing the x minus 1 over.
So you don't bring the other part over?
No, well, this other part, we just figured out up here that this part I underlined here
Yeah.
breaks down into x minus 1/2
Uh,
times this.
okay.
So I'm continuing to factor, but I want to keep reminding you guys, this is equal to the original polynomial. But see how you look at this and I go, oh, no sign changes, no more positive zeros. So if my three choices of 4, 2, and 0 polynomial, 4, 2, and 0 positive x-intercepts, I now know that it was 2. This x equals 1 and this x equals 1/2 are my only two positive intercepts. I know I don't have to go looking for irrational ones or anything else because there were no sign changes on this remaining factor.
So that's how you know there's no positive zeros, because there's
No more positive zeros other than the two we found. I'm applying Descartes' rule of signs here. Now, does that tell me anything about the negative zeros? Could this still have one negative zero in it? It could.
Wait, couldn't we just keep on dividing it?
But we have to. And this time our choices would be out of 6 and 2, but you know what? The more you remember from Algebra 2 and anything else we've done this year about factoring patterns, at some point you can abandon this technique. I haven't reviewed this with you guys yet, but any of you guys remember a little something called factoring by grouping?
Yeah, FBG.
Okay, Tyler, follow me over to this board. Problem is, I think are we about to get a mistake, or we're about to get a give me a sec. No, we're about to get a duplicate. Okay. All right. So, you got the whole board in this one, Tyler? Okay.
Yeah,
All right, thanks. Okay, so let's just look at just this factor. 2x cubed plus 6x squared plus 2x plus 6. What is the greatest common factor of these first two terms?
2 and 6. So
2.
that would be 2.
2. You're missing one.
2.
And 1.
2x squared.
Oh.
And then what's left is x plus 3, correct?
Mm-hmm.
Okay. What's the greatest common factor of 2x and 6 now?
Oh, that's 2.
It's 2.
Oh.
Now, x plus 3 in parentheses is a common single factor to both of these. And I get x plus 3 times 2x squared plus 2. And I don't have to pull out the synthetic division. If I did pull out the synthetic division, I could keep guessing if I wanted to. And negative 3 would work. Now this tells me that...
Wait, how are you getting 2x squared plus 2? Oh, because you're putting them together.
X
Oh, I
plus
see.
3.
Take the x plus 3
Yeah,
out
you
of
put the
each
other
term.
ones together. Okay.
Yep. I know, I should have taken I should have done that a little slower since I haven't seen that since last year. Now, if I'm looking for the solutions, I set each factor equal to 0, and this intercept is going to be x equals negative 3. What's going to happen here?
Let me think.
That will be...
Well, I'm going to get 2x squared.
equals 2.
2x squared equals negative 2.
So then you divide that by 2x
gotta have
squared
an eye on
equals
it.
negative 1. That's not real.
X is plus or minus I.
Wait.
Sorry if I rushed that a little bit. I'm looking at the clock. Any questions on this part? So, you could have kept going with the synthetic division if you wanted to, but it's usually faster if you start recognizing other factoring patterns. Will this always work when you get down to a cubic? No. Sometimes your only choice is to keep going with the synthetic division. But let's see how the fundamental theorem of algebra and Descartes' rule of signs worked out. According to the fundamental theorem, we should always have 5 solutions to a 5th degree polynomial. Did we start out with a 5th degree polynomial?
Mm-hmm.
And our solutions were x equals 1, x equals 1/2, x equals negative 3, x equals I, x equals negative I. If we're graphing this two-dimensionally, do we care about these two?
Nah.
No. But if we're not, we do. But the point is, the theorem is true. You always have 5 solutions. Just some of them are complex. A mix of real and imaginary.
Or in some cases not.
To a 5th degree polynomial.
Oh.
If we'd started with a third degree polynomial, you'd always have 3 solutions. But you don't always have useful solutions. Descartes' rule of signs Descartes' rule said that we would have, for the positive real zeros, we would have 4, 2, or 0 of them. Did that work?
Yeah.
How many positive solutions do I have that are not I?
Oh
Two.
no.
Two.
It didn't.
2.
Oh, because I is not considered. Yeah. Okay.
Yeah. So I got 2 real solutions on the positive side of the x-axis. And Descartes' rule of signs said 1 negative, let me specify, real 0. And did that work out? Did that work out?
Mm-hmm.
Yes, I just got the 1 of those. So there's my 1 real negative solution. Here are my 2 real positive solutions, and there was a total of 5. Was the fundamental theorem of algebra or Descartes' rule of signs particularly useful on this one? I would actually say no, because you guys guessed ridiculously well. If you get that lucky on the first ones and then it goes down to factoring by grouping, which most of them will. Actually, all of the ones that you guys did last night could have been done by factoring by grouping. Go back and take another look at them. You didn't actually have to do any guessing on them. I think all of them.
But the factoring ones were easy. Like it wasn't.
Yeah. But the you wanted to practice with the synthetic division anyway. So on this one, not so much. What if you got stuck and you hadn't found a negative number yet? I mean, this can tell you that you have to look for a negative one. You know what I mean? So these can be, I guess if you're unlucky, Descartes' rule of signs and the fundamental theorem can be more helpful than not. But this pattern will work for every polynomial you can imagine. Any questions on either of these? Fundamental theorem or Descartes' rule of signs?
Basically, this gets you the same thing as what we did yesterday.
Well, if you're unlucky, this can speed you up, slow you, or help you double check. If you're not really lucky with the guesses and seeing factoring patterns.
Okay.
This can tell you what you're looking for.
So like on tonight's homework, though, we should just do this.
Yeah,
Okay.
and some of them say, like on tonight's homework, the directions actually say, find the number of positive real zeros, the number of possible negative real zeros first. So you have to give me these possibilities, just to show me you can use the rule.
By the way, what's the homework?
By the way, the homework is page 234.
I feel like the camera isn't zoomed in enough. Like I feel like it's not.
It's a wide angle lens, but hopefully it's a high enough screen resolution that people can see it or zoom in or take a screenshot of it. Page 234, 17 through 23, all. Questions, comments, concerns, or compliments?
You know I'm not here tomorrow.
Yes. Yes.
Senior skip.
Seen.